All right, in this video, we're going to be talking about exponent properties. And I know you have already heard about these exponent properties, and we're going to be looking at them through a slightly different lens, talking about exponential functions. So we're going to talk about also some transformations of exponentials. Okay, so what I need to do is just go back to reminding you about x to the 2 times x to the 3. We've kind of already done this in this class before, but we're going to get x to the 5 from this. And for the reason, you might have a different reason for like how you understand this to be true. But I think the easiest reason is to think about x squared times x to the third as, x times 3x's, which is a total of 5x's multiplied together. That's going to be x to the 5. I think that's the easiest way. And then what it says below is that the product property for exponents states that if we're multiplying two numbers and they've got the same base and different exponents, that's where we're just going to add the exponents. Okay, and graphically, this property implies that every horizontal translation of an exponential function is equivalent to a vertical dilation of that same function. Okay, possibly by a different factor, but that they are actually the same. I think the best way to convince you of this is just to show it to you in action. So I'm going to start off with f of x equals 2 to the x, and then g of x is going to be 8 times f of x. Okay, so I'm just going to work along the left. I'm going to say, all right, the transformation from f to g that would be most obvious from what we're seeing from g of x equals 8 times f of x, we're multiplying on the outside. Multiplication is a dilation, on the outside is vertical. So it's going to be a vertical dilation by a factor of 8. But if we kind of like dove in and tried to write a formula for g of x and then applied that exponent property I was just reminding you about, we might see that we could look at this as a different transformation. So if g of x is equal to 8 times f of x, g of x is going to be 8 times 2 to the x. And we've seen exponential functions like that just even recently. But what I'm going to do is recognize, wait, 8 is a power of 2. So I'm going to rewrite that as 2 to the third times 2 to the x. And then I'm going to say if I'm multiplying two things with the same base and different exponents, that's where I'm going to add the exponents. So 3 plus x, that's like x plus 3. And all I did was just apply that exponent property. So this is still g of x. I didn't do anything to it. Just changed the way it looked. And so an equivalent transformation from f to g would be like, well, f of x is 2 to the x and g is 2 to the x plus 3. It's like replacing x with x plus 3. And remember, that's a horizontal translation. That would be left 3 units. Okay, so I would say that we could look at this 8f of x and, well, f of x plus 3, they're actually the same thing. But we could look at, g as the transformation of f two different ways. That's what I'm saying is for the curve y equals 2 to the x, these two transformations are equivalent. So I pulled up a Desmos window here for you to look at, and so I graphed y equals 2 to the x. And then I've got this g of x equals 8 times 2 to the x, 8 times f of x, and maybe I'll just show you that right here. Okay, so that's going to graph in blue. Okay, and notice right there, it looks like it shifted to the left 3 units. Why is it going only every other one? There we go. Those are the grid lines I needed to see. We're shifting left 3 units. You can look at the y-intercept on the red, and then that 0.3 to the left of it. Okay, but also, you could look at this as a vertical dilation by a factor of 8, right? Look at the y-intercept was 1, and now it's 8. Okay, and moreover, when I go and graph y equals 2 to the x plus 3, oh, wait, whoops, no, I graphed 8 times 2 to the x, and it looked like it just shifted it over 3, which is exactly what I'm trying to say. But if I graph x to the, or 2 to the x plus 3, it gives me the same curve. The green goes on top of the blue. That's what I'm trying to tell you, is that this is why these transforms are equivalent. They generate the same curve. I don't think there's a whole lot of understanding to be had out of the nature of the curvature and stuff. It's actually easiest to see algebraically why these things are true, like what you can see on the screen right now. I think that's the most obvious. And then on the right, we've got h of x equals f of x minus 4. Okay, so f of x minus 4, that's going to be a shift. And since I'm subtracting 4, that'll be going right by 4 units. If we went to write a formula for h of x, I'd say, all right, well, h of x is f of, so that's 2 to the power of x minus 4. Replacing x with x minus 4 wherever I see it in the formula for f. Okay, so h of x is 2 to the x minus 4 power, and now I'm going to apply this exponent property in reverse. So I'm going to say that this is equal to 2 to the x times 2 to the negative 4, and I'm going to just remind you that 2 to the negative 4 is not, it's going to be times 1 over 16, right? 1 over 2 to the fourth power. And that's going to be equal to 1/16 of 2 to the x. And looking at 2 to the x versus 1/16 of 2 to the x, looks like I've just multiplied on the outside by 1 over 16. So we would say that would be a vertical dilation by a factor of 1/16. So it turns out for, the curve y equals 2 to the x, a shift right by 4 is equivalent to vertically dilating by a factor of 1/16. But, most easily understood in terms of the algebra right here, what you can see, how we transformed the one equation to another, just using the algebra properties, right? Not actually changing anything. All right, here we got a couple of problems, and the problems on this page are based off some multiple choice problems I need you to be able to solve here before too long. And the first one's like, all right, f of x equals 9 times 3 to the x. This can be rewritten as f of x equals 3 to the x plus k. What's the value of k? So what we're going to do is we're going to apply the exponent property. So I'm going to say, all right, this is equal to 9 is a power of 3. That's 3 to the 2 times 3 to the x. Same base, different exponent. We're going to add the exponents, 3 to the 2 plus x, or x plus 2. And that's showing me that the number I'm interested in, k, that's just going to equal 2. G, I think, I would just have you try this on your own, but I don't think it's going to take all that long. So I'm just going to say k times 2 to the x. Well, I'm going to apply the property in reverse. 2 to the x times 2 to the negative 3. And that's going to be 2 to the x times 1 over 2 to the third. And that's going to be 1/8 of 2 to the x. And then I'm going to say, all right, k is that number out in front, so I'm going to say k equals 1/8. All right, and then this next one is saying h of x is 5 to the x. Write an equation for each function which is formed by transforming the graph of h. And so this is one I think you should try on your own to remind yourself, like, hey, am I good on transforms or do I need to go back and review? Either way, it's fine, right? It's just transforms. You learned about them last year. We've already done a little bit this year. We're going to continue to do them, so it's not like the most urgent thing, but it's something you need to be pretty fluent in. See if you can write down a formula for these and check your answer against mine, which is going to pop up here in 3 to 5 seconds. All right, there you go. So the first couple, these are written in some language that I wouldn't personally use. But I have seen this this type of language in AP Classroom for AP Pre-Cal on a multiple choice question. So that means that this is language you need to be familiar with. So a horizontal translation of the graph of h by a units, positive a units, that does mean going to the right. Okay, so we're going to say replace x with x minus a. So I've got 5 to the power of x minus a, which is equivalent to 5 to the x, 5 to the negative a, or 5 to the x times 1 over 5 to the a, whatever you like, right? I just wanted to make sure that, whatever you'd written down, if you'd written it down correctly, that your answer was somewhere on the screen. And for a horizontal translation negative a units, that does mean going to the left by a. And so we're going to replace x with x plus a. And so 5 to the x plus a, that can be written as 5 to the x times 5 to the a, and I think that's all I can say about that. And for the vertical dilations, by a factor of a, we're just multiplying by a, or 1 over a in the case of d of x. But there's really not anything else we can do with that unless we knew that a was, I don't know, maybe a factor or a power of 5. Or a factor of 5, I guess. But yeah, without knowing more about a, there's not going to be anything else we can do with these. The last of these examples is g of x equals f of x divided by 16. Describe two equivalent transformations of the graph of f that give the graph of g. Okay, so, in multiple choice, probably which of these describes a transformation of the graph of f that gives the graph of g. And the one that you want isn't going to be on there, right? The one that's immediately obvious from looking at it, okay, f of x over 16, vertical dilation by a factor of 1 over 16. That's not going to be one of your answer choices. They probably have vertical dilation by a factor of 16, or something else, lots of other things, but not that one. We're going to need to say, all right, first thing I can see is the vertical dilation by a factor of 1 over 16. But if I go in and look at 4 to the x over 16, That's 4 to the x over 4 to the 2. And we don't really need to talk about the subtraction property of exponents, but it's 4 to the x times 4 to the negative 2, or you could look at it as subtraction if you remember that from algebra 2. Either way, you're going to end up with 4 to the x minus 2. So from there, that would look like a translation of the graph of y equals 4 to the x. So I would say translates right 2 units. And so the red descriptor and the blue descriptor, these are two equivalent transformations of the graph of f that both give the graph of g. Okay. Now with the power property of exponents, we haven't really talked a lot about horizontal dilations in this class besides to say, hey, we're not doing those yet. And we're still not really doing them. The power property for exponents says that, if you're taking power over power, we're going to multiply the exponents. I know y'all are aware of this. We've done this in this class already. Okay, I would say the best reason would be because x squared to the third is going to be x squared times x squared times x squared, and use that addition property that we were just talking about. That's going to be 2 plus 2 plus 2 is x to the 6. To see, but you might have your own way of understanding why that's x to the 6 and not x to the 5. And if it's different from that, then that's what you should write in that spot there. Okay, but it says we're going to multiply the exponents. Graphically, this property implies that every horizontal dilation of an exponential function is equivalent to a change of base of that exponential function. And we don't really need to know what change of base looks like. And we've decided, pre-cal teachers at my campus, we're going to talk about horizontal dilations later when we have trig graphs, and actually it makes more sense to horizontally dilate things. And so we're going to just use this as an opportunity to talk about a reflection across the y-axis. Okay, so if I have the point right here, x and y, and I replace x with negative x, but keep y the same, what's happened is I've just reflected across the y-axis. So y equals f of negative x, replace x with negative x, that's a reflection across the y-axis. So let's just get to it and look at one of these. So consider the function f of x equals 4 to the x, and let g of x equal f of negative x. Okay, we'll start with a sketch of the graph of f because that's exponential growth. We know what that looks like. We did that in the last lesson. Okay, with g of x, if g of x is f of negative x, and we just said that that causes a reflection across the y-axis, we're going to basically take this thing, there it is, and do that to it, right? So we need to be horizontally flipping. That's another way of thinking about it. Pivoting around the y-axis. Pretty much what I'm saying is that this piece of graph is going to need to go to the right of the y-axis, and that piece of graph is going to need to go to the left of the y-axis. And, I mean, it's not quite as good as the one on the left, but I think it's going to be good enough for our purposes here. But what I do want to point out is if this is exponential growth right here, and I flipped it around the y-axis, that I would be looking at exponential decay on the right. Okay, and we're going to see that algebraically when we rewrite g in the form g of x equals b to the x. All right, so I'm going to kind of just copy what I've got in here. F is 4 to the x. G of x is equal to f of negative x. So wherever I'm seeing x in the formula for f, I'm going to be replacing it with negative x. So that means that g of x is going to equal 4 to the negative x. And there we go. Wait, that's not b to the x, that's b to the negative x. So what I need to do is apply that multiplication property of exponents. I see multiplication with the negative and the x. That's negative 1 times x. So negative 1 times x. And then I'm going to apply the power property in reverse and say that's 4 to the negative first power to the xth power. And then I know what 4 to the negative 1 is. That's 1 over 4. So I can conclude that my rewrite of g is going to be 1/4 to the x. And that was what we had described last time as exponential decay, when our common ratio, the number that was getting raised to the xth power, when that was between 0 and 1, we were going to be seeing exponential decay, and that's what we're seeing right here. So that's confirming what I thought was happening with the graph. And in general, if you have a base that's greater than 1, the function f of x equals a to the negative x That's going to represent exponential decay for reasons I just went through right here. But I'll also say, other examples of that would be like y equals 2 to the negative x, or 3 to the negative x, or 5 to the 2 minus x, right? If we have really a negative x power of a number that's greater than 1, we're going to be seeing exponential decay. Right, these next two examples, I didn't do these in class, but they look kind of interesting. So if f is rewritten as f of x equals 25 times 3 to the ax, so that's where we're just manipulating the 9. Well, 9 is a power of 3, so I guess I should probably start with that. 25 times, I don't know how obvious these are to y'all. I feel like this one's really obvious, but it might not be to you. So I'm going to just work through all the steps on this one. So 9 is 3 to the 2. And so it was 9 to the x, 25 times 9 to the x. And then I'm going to apply that exponent property forwards and say, well, that's 3 to the 2 times x, right? We're going to multiply the exponents when we're taking power of a power. And so, yeah, that means, right, okay, I was looking for the multiplier on x and the exponent of 3, and that was 2. So I'm going to say a equals 2. And then if f is written as f of x equals 25 times 81 to the bx, that's fun. Okay, this is different. I don't remember adding this problem on there, but this is a good one. So we need to manipulate the 9 to the x, and like, wait, how am I going to write 9 as power of 81? And it's like, well, 9 is the square root of 81. The square root is the 1/2 power. That's where we're going to multiply these exponents together. So that would be 25 times 9 to the 1/2 x. And there it is. That's the value of b. And that was, I don't know, didn't remember that one. The last thing I need to tell you about today is e. And this is a number that hopefully you heard a little bit about in Algebra 2. Hopefully your Algebra 2 teacher reassured you it's just some weird number between 2 and 3 that we happen to be interested in later courses, and it's a real number and it's not anything to be scared about. That's what I always say. But I copied in the text from the AP Pre-Cal course description, which is similarly vague. It says the natural base e, which is approximately 2.718, is often used as the base in exponential functions that model contextual scenarios. And I actually think that really encapsulates it well. If you're interested in, what E represents, go look in my Algebra 2 playlist for exponential functions. I talked a little bit more about other definitions of it. But I'm not going to be doing that here, because what you need to know for AP Pre-Cal is, let me copy it in. So once again, it is a constant. It is a number and not a variable. It is between 2 and 3. I'm pretty sure in pre-cal, if you just assumed it was 2.5, your experience might not be any different as long as you use the E button on the calculator and the natural log button when that time comes. And then third fact, it is not something you need to be scared of. And I'm going to try to work that out to y'all. I think that was more of, a couple of years ago when people didn't really take Algebra 2 because they took it on the computer. They were a little bit more scared of E because they were scared they were going to face the consequences of their choices a few years back. But we all have to face the consequences of our choices. So G is given by g of x equals 2e to the negative x. So this is kind of combining the last two things I've told you about, which was e and the negative x power of a number bigger than 1, which is causing exponential decay. So I'm going to draw a picture of that. So we've got a picture of it, and so we're going to be asked to use limit notation to describe the end behavior of this function, and so that's going to be two limits. We're interested in the limits of g of x as x approaches infinity and negative infinity. Those are our end behaviors. So over here, I'm going to look as x approaches positive infinity, it looks like g is approaching 0. So I'm going to put that in here. Now I'm going to also point out that a different way we could understand that is thinking of 2e to the negative x as 2 over e to the x, which is exactly the type of fraction that has a numerator that's constant and a denominator that's growing, which does approach 0, right? Now, over here on the left side, as x approaches negative infinity, that's where g of x is going to be approaching positive infinity. And you could think about, putting in a really large negative number in for negative x. I'd be taking e to a large positive power. E is a number between 2 and 3. That's going to give me back a really large output. Okay, so I think, yeah, that's all I've got for you for this video. I'm sitting at 20 minutes. This is perfect. That's all. Thanks for watching.